As of the year 2025, approximately 135 million monitors are shipped to markets worldwide every year. This includes both new models and replacements for old ones, as part of a typical 4 to 5 year tech upgrade cycle. While it is difficult to pinpoint the exact number of monitors in global use, due to varying lifespans and growing demand, it is estimated to be in the billions. That is because as much as 66% of the global population uses computers. But what happens when it is time to recycle a monitor? Cathode ray tube monitors, those old bulky screens, were common before flat screens took over. They contain glass with high lead content, phosphors, and electronic components. Lead in the glass can make up as much as 20% of a monitor's weight. Sounds dangerous, right? Light-emitting diode, or LED monitors, are the modern flat screens that use LEDs for backlighting. They are lighter and more energy efficient, but still contain plastic, metal, and rare earth elements. Guess what? Mishandling these monitors can cause serious environmental problems. Lead from CRTs can leak into soil and water, and plastic from LEDs can take centuries to decompose. That is why recycling is not just a trend, it is a must. In the United States, over 4,400 million pounds of e-waste is generated every year, but only 25% is recycled locally. Every single day, Americans throw away more than 500,000 computers and mobile devices. This creates a massive environmental challenge. Electronic recycling centers, like Repowered in Minnesota, play a key role in addressing this issue. Each year, they process about 3 million pounds of electronics, which makes up 5% of all electronic waste collected in the state. Impressive, right? These centers accept any device with a cord, except for large appliances, and ensure proper disposal or reuse. Some states, like California, go even further. There, it is illegal to dispose of e-waste in regular landfills. California has over 600 drop-off locations, and recycling is funded through a fee on the sale of new monitors and televisions. By the way, California spans around 163,696 square miles. It is the third largest state. Trucks are loaded with old monitors and driven to recycling centers. This method is typically used for short and medium distances. For long hauls, container shipping is used. It is more cost-effective and safer for large volumes of electronics. At the plant, monitors are unloaded in the intake area, where trained staff inspect them for hazardous materials and evaluate their condition. The monitors are disassembled into key components, such as cathode ray tubes, display panels, power supplies, and other electronics. This process can be done manually or with specialized equipment. The separated parts are sorted by material type. Casings, power supplies, and other metal components are separated for further recycling. Recycling metal parts from monitors looks like a full-on industrial operation. Massive machines work in sync to turn scrap metal into something new. Shredders roar. Furnaces blaze. The air is thick with the scent of molten metal and the noise of industry. Metal components are cleaned of contaminants like paint, plastic, and other non-metallic materials. This is done with machines that strip away surface layers and boost metal quality. Rotating brush systems or dedicated surface cleaning machines are used. This step can also involve shredding, crushing, or other mechanical methods. Metals might also be treated with chemical solutions to remove corrosion and other residues, using acids or alkaline solutions to dissolve unwanted layers. Then, the metal is shredded into smaller pieces using large presses or industrial shredders. This makes it easier to process and transport. Next, metals are sorted by type. Ferrous metals are separated from non-ferrous ones. Each metal type requires a different recycling process. The metal pieces are then melted down in giant furnaces at high temperatures. Steel melts at about 2,552 degrees Fahrenheit, while aluminum melts at around 1,112 degrees Fahrenheit. As the metal melts, impurities are removed, and the material is poured into molds to form new ingots. These ingots are used to manufacture new metal products like construction materials, car parts, or home appliances. Using recycled metals cuts production costs and preserves natural resources. At smelting plants, huge conveyor lines move metal pieces through different recycling stages. Workers in full protective gear oversee the process to ensure safety and quality. Thanks to this effort, old monitors are reborn as new, useful products, helping the environment and advancing sustainability. Plastic components from monitors and other electronics are collected and sorted by type, usually polycarbonate, acrylic, and polystyrene. They are shredded into small pieces using machines like industrial shredders or crushers. This makes the plastic easier to transport and process. The shredded plastic is then cleaned to remove contaminants and impurities. This step uses air jets, magnets, or other tools, depending on the plastic type. The clean, shredded plastic is melted and molded into pellets. These pellets become the raw material for making new plastic goods. In the United States, about 6,600,000 pounds of plastic are recycled annually. That is only around 8% of total plastic waste. But those recycled pellets go on to make more than 100 million new plastic items every year. Shredders and crushers roar as they grind plastic. Conveyor lines move the material through different stages of processing. Recycling plastic saves about 88% of the energy compared to producing new plastic from raw materials. A typical CRT monitor contains almost 3 pounds of lead in its glass. The leaded glass is separated from the monitor's other components. The cathode ray tube is disassembled into individual parts: the screen, the funnel, and the neck. The screen is made of activated glass, while the funnel holds the lead. The glass is cleaned of phosphor and other residues using chemical solutions or mechanical methods. After cleaning, the glass is homogenized. During this stage, you can see giant rotating drums scrubbing paint and resins from the surface. The glass is then sorted by size and sent off for further processing. Thanks to this method, old leaded glass gets a new life while supporting sustainable development. The glass is melted down in special furnaces at high temperatures. Lead is extracted and purified from impurities. This clean lead is used to manufacture new products like batteries, ammunition, or building materials. So yes, it is possible your old monitor might one day help protect the country. Now let us move on to recycling circuit boards. Printed circuit boards are shredded using machines like hammer mills or industrial shredders. This helps extract most of the metal content. The resulting material is usually smaller than 2 inches in size. This shredded material is passed through magnetic separators and air jets to separate metal from non-metal elements. Metals like copper, gold, and silver have unique physical properties that allow for efficient separation. Chemical extraction methods are used to recover the metals. For example, gold and silver are dissolved using acidic solutions. These solutions are then processed to obtain pure metals. Another method involves heating the circuit boards to high temperatures to burn away the non-metal materials and extract the metal content. However, this method can release toxic gases, so it is used with strict safety measures. During chemical recovery, you might see massive tanks filled with acidic solutions where metals are being separated. After extraction, the metals are purified and formed into ingots for manufacturing new goods. Through this process, old circuit boards are reborn as new, useful materials, supporting sustainability and protecting the planet. LED display panels can be recycled for use in making new screens or other electronic components. While the process is complex and not always cost-effective, it is seen as a promising path forward. Some LED monitors contain rare earth elements, which can be extracted and reused. Recycling LED monitors saves up to 70% of the energy compared to making new items from raw materials. What do an old iron and thousands of dollars have in common? That is right, copper. You know, just from one single cord, you can pull out enough copper to make brand new electronics. Every day, tens of thousands of old irons are recycled around the world, taken apart down to the very last screw. But how exactly does this happen? Why can even the sole plate be dangerous? And what is hiding inside the heating element? I am about to show you how dead irons come back to life, from being taken apart to becoming valuable raw materials. Like other electronic appliances, irons are accepted at special electronics collection points. There, they are sorted into categories: those that can be repaired, those that need to be disassembled for parts, and those sent for complete recycling. Worn out or non-working irons are sent to recycling facilities, where the disassembly process begins. When an iron arrives at the disassembly line, specialists wearing protective gloves check it over. Some parts, like the heating elements, can be hazardous due to residual electrical voltage or toxic substances. First, they remove the electrical cord. Its insulation is usually made of synthetic plastic or rubber, and inside there is copper or aluminum wire. Synthetic plastic is durable, flexible, and water-resistant, but when heated or burned, it can release toxic substances, including dioxins, which are harmful to the environment and human health. That is precisely why disposing of it requires special methods. The removed cord is not just set aside. It immediately goes onto a sorting line. First, it is chopped up in a special shredder into pieces about 1 to 2 inches long. This makes it easier to separate the metal from the insulation later on. Next comes the material separation. This is usually done using mechanical or electrostatic sorting methods. What does that mean? What kind of fancy words am I throwing at you here? Look, the copper and aluminum wires are separated and sent off to metallurgical plants for melting. The shredded plastic or rubber goes for recycling, for example, to make new cable insulation or other products. If the insulation contains harmful additives, it might be incinerated in special furnaces equipped with filters or sealed away in a landfill. Separating the copper and aluminum from the shredded electrical cords happens in several stages. So, after the cord is shredded, the pieces are sent to a granulator. This is a special grinding machine that breaks down the pieces of wire into even tinier particles, measuring about 4/100ths to 8/100ths of an inch across. This is how the metal and plastic get separated. Next, the mixture goes into an air separator. This uses a stream of air that lifts the lighter particles up, while the heavier ones fall down. This way, the plastic is separated out even before the main process. If there are any steel components in the wires, like a thin shielding layer or reinforcing fibers, they are removed using a magnetic conveyor belt. But the tricky part is, the little pieces of aluminum wire and copper wire get mixed together, so now they need to be separated. To do this, the metal particles are sent into a metal drum that is charged with high voltage. Copper has different electrical conductivity properties than aluminum, so under the influence of electrostatic forces, they bounce off in different directions and are collected in separate containers. After sorting, the materials are checked again, either by hand or using automated systems. Copper, which is 99% pure, is melted down at a temperature of 1979 degrees Fahrenheit and used for new cables. Aluminum melts at 1220 degrees Fahrenheit and is used to make parts or casings for electronics. This process allows up to 95% of the metals from the cords to be reused, reducing the need to mine new raw materials. Meanwhile, back at the iron, the housing is unscrewed. This could be a plastic or metal shell, depending on the model. A worker wearing gloves firmly secures the device on a table coated with a thin layer of metal shavings, leftovers from previously disassembled appliances. An automated screwdriver mechanism, humming almost silently, moves toward the first screw. The bit fits precisely into the screw head, makes a few quick turns, and the loosened screw flies out into a special container, clinking against the sides. The housing still holds on, as if resisting its fate. But the hands of the technician, seasoned by thousands of these operations, know how to make it give way. A slight pry with a tool under the edge of the housing, and there is a familiar click, like an old machine sighing. The plastic cracks, yields, and then splits into 2 parts, revealing the device's insides. If the housing is metal, it all happens with different sounds. The metal screws fall heavier. The housing slides across the table with a dull clatter. Sometimes, special cutters have to be used, Sharp blades sink into the thin metal, leaving behind jagged edges that glint under the lights. Finally, the shell is removed, and the device, just a moment ago solid and sealed, seems almost vulnerable. Its insides exposed, ready for the next stage of disassembly. Once the housing is off, the heart of the device is revealed. The circuit board and the heating element connected by a network of thin wires. They are like the veins that powered the appliance in its former life. Tweezers with pointed tips move towards the first contact point. A gentle tug, and the wire pulls away from the board with a faint snap, exposing a tiny copper core. Another tool, resembling a miniature pry bar, slips under the edge of the board. A little pressure, and the board pops out of its place, leaving behind a web of connectors and mounting points. The heating element is the next hurdle. If it is ceramic, it sits inside like a white heart, sometimes coated with a grayish film from countless heating cycles. If it is a nichrome coil, it is wound into a delicate spring, resembling a dried leaf. It is removed carefully to avoid damage, because even the smallest break can complicate further processing. And just like that, with a few more movements, the once unified mechanism falls apart into separate components. The circuit board and heating element are separated, ready for sorting and further processing or disposal. The last part holding its ground is the sole plate. It has absorbed thousands of heating and cooling cycles, signs of use, scratches, and faint traces of scorch marks. It is the sturdiest part of the device, and removing it is not so easy. To get it off, they take a tool similar to a thin pry bar and wedge it between the main body and the sole plate. A barely perceptible push, and you hear a characteristic scraping sound as the metal begins to yield. If the sole plate is aluminum, it bends under pressure, making a slight crunching sound. A ceramic one stays put until it gets a precise tap, after which it separates from the body with a muffled thud. If it is stainless steel, it puts up the most resistance. It often has to be unscrewed by hand or pried off using special levers. Finally, the sole plate is detached. It drops onto the metal table with a dull thud, leaving traces of grime on the worker's fingers. This is the last major piece, and now the appliance is completely disassembled, ready for further sorting and recycling. Every year, the United States spends $17 billion just on importing fresh fruits, and avocados from Mexico alone rack up $3 billion of that. The sugar in your cup of tea? Chances are, it traveled thousands of miles from Latin America. Americans chow down on 1 billion pounds of tuna every year, and 90% of winter tomatoes come from Mexico, where agricultural cartels are battling it out for control of that market. From olive oil out of Spain to turmeric from India, imports keep the United States fed with variety and savings. In this video, we're going to spill the beans on where your favorite foods come from, the numbers behind their journey, and why it matters to every single one of us. Don't miss it. It's going to be tasty and full of surprises. Get comfy. Brew yourself some tea. Do you take it with sugar? Well, that sugar probably came from another country just for you. Even though the United States produces its own sugar, demand often outstrips supply, making imports a must. The United States is a huge sugar consumer. Plus, producing sugar in some countries is cheaper thanks to better climates and lower costs, which makes importing a smart move. The big players supplying sugar to the United States are countries in Latin America and the Caribbean, especially Mexico, which gets a sweet deal on the American market thanks to the North American Free Trade Agreement. Closing some borders in 2025 wasn't meant to mess with legal trade between the United States and Mexico. Still, it might have slowed down logistics and caused delays in getting goods like sugar across. The European Union is a key supplier of seafood to the United States of America, keeping the American market stocked with all kinds of fish and shellfish. This helps meet demand for seafood in the United States and keeps the supply steady. Spain and Japan are major players when it comes to fresh and frozen tuna for restaurants. Tuna is one of the most popular seafoods in the United States. Americans eat about 1 billion pounds of it a year. That makes the United States one of the world's top tuna consumers. Thailand, Indonesia, and Vietnam are the go-to sources for canned tuna, the most affordable and in-demand option. You'll find it in salads, sandwiches, or just as a quick snack. French oysters and other shellfish are a hit with American eaters too. The Netherlands pitches in with fish shipments to the United States as well. Every year, the United States shells out more than $17 billion just on fresh fruit imports. The biggest supplier? Mexico, covering over 40% of all fruit imports to the United States. Importing means supermarkets can offer a huge variety of fruits no matter the season. Americans eat more mangoes, pineapples, and avocados than they can grow at home. Plus, bringing them in from countries with cheaper labor often beats growing them domestically. Take avocados. Mexico supplies over 90% of the avocados imported to the United States. Each year, Mexican farmers ship over 2,640,000 pounds of avocados to the American market, worth about $3 billion. Most of those avocados come from Michoacán, where the climate's just perfect for growing them. Every year, the United States imports over 880,000 pounds of olive oil, costing around $1.5 billion. Demand's climbing thanks to the Mediterranean diet craze and the push for healthy eating. Drop a comment below. Do you go for healthy eating too? Meanwhile, American producers, mostly in California, are trying to ramp up their own olive oil output, but it's still a drop in the bucket compared to Europe. Spain leads the pack, supplying over 40% of the olive oil imported to the United States. Spanish oil's a favorite for its quality and decent price. Italy, which used to rule the American market, now sits in second place with about 30% of imports. Greece and Tunisia are stepping up too, especially in the premium oil game. The most popular cheese in the United States? Mozzarella. It makes up about a third of all cheese eaten here, thanks to being the star of pizza, one of America's favorite foods. Cheddar's a close second, showing up in sandwiches, burgers, and mac and cheese. The United States churns out over 13,200,000 pounds of cheese a year, but it still imports premium kinds too. Top suppliers include Italy, France, the Netherlands, Switzerland, and Spain. Each year, the United States brings in over 352,000 pounds of cheese, worth about $1.5 billion. Most of it ends up in restaurants and gourmet shops since real European cheeses cost a pretty penny here due to tariffs and shipping. Parmesan's a big name and a fan favorite in the United States. The country imports over 22,000 pounds of it yearly, though a lot gets used pre-grated. The real Parmigiano Reggiano's pricey, so the local knockoff, Parmesan, made with simpler methods, is way more popular. 70% of tomato imports come from Mexico. Mexico supplies nearly 100% of the fresh winter tomatoes in the United States since its climate lets them grow year-round, while American production tanks in the cold months. U.S. farmers grumble about cheap Mexican tomato imports, and trade spats between the two countries have flared up more than once. Most of those tomatoes roll in through Florida, but they compete hard with local ones, putting political heat on the U.S. government to cap imports. Texas border crossings handle millions of tomato crates every year. For example, over 50,000 trucks loaded with tomatoes pass through Laredo alone annually. Mexico sends over tons of cherry and Roma tomatoes, loved by Americans for their sweetness and cooking convenience. Oh, and in Mexico, powerful agricultural cartels run the tomato show, sometimes sparking criminal showdowns over market control. Canada's the third biggest food supplier to the United States, trailing only Mexico and the European Union. What do you think? Could we lose such a major importer anytime soon? Key categories include meat, grains, dairy, fish, and veggies. Canadian pork exports to the United States top $2 billion a year. Canada's also a big beef supplier, especially after mad cow disease caused some hiccups. But chicken? Nope, Canada's not sending that over. A bird flu outbreak wiped out poultry and slashed egg supplies big time too. Being right next door, Canada cuts down on shipping costs for the United States. Plus, their quality standards match what the American market demands. China sends a hefty chunk of food to the United States, though it's a smaller slice of their imports compared to electronics or clothes. China's a top seafood supplier, especially tilapia, shrimp, cod, and canned fish. It's also the world's biggest garlic grower, and a lot of that heads to the United States. Then there's green tea, black tea, and honey coming over too. Americans love Chinese rice noodles, sweet potato vermicelli, and wheat noodles. Demand for Asian foods has shot up over the last few decades, thanks to Asian restaurants, street food, and the healthy eating trend. Rice and sweet potato noodle consumption in the United States is up 20% in the last 10 years, driven by the gluten-free craze. The United States is one of the biggest importers of Indian spices. Top picks include turmeric, cardamom, cumin, coriander, chili pepper, and cloves. India produces over 80% of the world's turmeric, and a big chunk of that lands in the United States. Oh, and India is the second largest tea supplier to the United States after China, with faves like Assam, Darjeeling, Nilgiri, and masala chai. India is the main source of basmati rice for the United States too, perfect for healthy eaters and Indian food fans. The United States brings in tens of thousands of pounds of legumes from India yearly as vegetarian diets catch on. Mangoes? A total crowd pleaser. India ships over 33,000 pounds a year. Demand for Indian goods is booming thanks to healthy eating trends, exotic flavors, and the rise of Indian cuisine in the United States. You might wonder, why all this importing? Doesn't the United States grow broccoli or spinach? Sure, but don't forget those harsh winters in some regions. Imports dodge seasonal shortages, keep prices down, and bring variety. In summer, California, the United States' veggie powerhouse, has huge harvests, but winter cuts production way back. Cheaper labor abroad helps too. Growing and freezing veggies in places like Mexico, China, or Peru costs less than doing it in the United States. It's easier to ship frozen veggies over. They last longer and keep their nutrients, making them perfect for restaurants and big stores. Take broccoli. It holds on to its goodness when frozen. It's a legit superfood, packed with nutrients and proven health perks. Even though the United States is a top tofu exporter, it imports plenty too to meet demand. About 1,585 importers bring tofu into the United States, keeping the market stocked with options. Tofu imports have doubled in recent years. Made from soybeans, it's a protein-packed powerhouse. Tofu's a big deal in global trade, thanks to its nutrition and appeal to all kinds of eaters. The United States plays both sides as a major exporter and importer, showing how much Americans crave it. Beyond foodies and health nuts, athletes and bodybuilders dig tofu too. It's clutch for building and recovering muscles. Have you ever seen a ship that does not touch the water? Now, imagine that such a vessel not only exists, but can also carry tens of tons of cargo and accelerate up to 250 miles per hour. Meet the hovercraft landing craft, a unique combat vehicle that glides above water, land, sand, and even ice. Its engines are just like those in fighter jets, and its maneuverability lets it drift on waves. But how much does this technology cost? How do they build it? And why are even seagulls afraid of these machines? Let's find out. The idea of using an air cushion came from the British engineer Christopher Cockerell in the 1950s. He experimented with airflows using tin cans and a hairdryer, ultimately creating the concept of a vehicle that could glide over any surface. In 1959, the world's first real hovercraft was launched. Later, this technology found its way into military use, specifically in LCAC-type landing crafts developed in the United States during the 1970s. So, Cockerell invented it, but the military refined the idea into its modern form. Let's move forward. Or maybe sail ahead. Manufacturing hovercraft landing crafts involves several stages. Initially, design bureaus create drawings and digital models of the craft. The design process depends on whether it's a new project or an upgrade of an existing one. Creating a completely new hovercraft takes from 6 to 12 years. Imagine that. Preliminary design and concept stages last from 1 to 3 years. Developing drawings and digital models adds another 2 to 5 years. Building and testing the prototype takes an additional 3 to 5 years. Finally, we get a ready-to-use craft. If we're talking about upgrading an existing design, the process takes half the time. Analysis and adaptation of drawings take from half a year to 1 year. Updating digital models takes only 1 or 2 years. Building and testing the updated version takes 2 to 3 years. The newest American hovercraft, called the Ship-to-Shore Connector, replacing the LCAC, began development in the 2000s. The first test models were ready in 2012 and 2014, but full-scale production started only in the 2020s. The process is lengthy because these crafts must be reliable, fast, and suitable for challenging operational conditions. After drawings and digital models are developed, suppliers of materials and components are selected. The military announces tenders, where companies compete for contracts. Manufacturers must pass certification and prove their materials withstand extreme conditions. Some components are produced exclusively domestically for national security. Thus, the process is complex but critically important. If even one component fails, the entire mission can be jeopardized. The craft's frame is assembled at shipbuilding yards. These massive industrial complexes are usually located on coastlines or near large rivers. They cover areas from dozens to hundreds of acres, since multiple vessels must be built simultaneously, with space for storing materials and heavy equipment. There are huge covered or open areas where ship hulls are assembled. These areas can be from 500 to 1,500 feet long to accommodate large structures. In metalworking workshops, aluminum alloys for the LCAC hull are cut, welded, and shaped using robotic machines and laser cutting. Shipyards also include dry dock basins, enormous artificial pools, where finished crafts are tested before launching. Massive gantry cranes with lifting capacities from 100 to 1,100 tons move large sections of hovercrafts. Additionally, there are areas for installing gas turbine engines, radar, and navigation systems, as well as logistics yards, where incoming materials and components from suppliers are stored. One of the largest such shipyards in the United States has been building military vessels for more than 100 years. The frame assembly of a hovercraft landing craft is constructed mainly from aluminum alloys, using welding and assembly methods different from traditional shipbuilding. Aluminum sheets and profiles are supplied as ready-made blanks. Robotic machines cut out parts according to computer-generated drawings. Sections for the future frame are prepared in special workshops. The LCAC structure is not assembled entirely at once, but built from large modules. Each module, for example, the bow, stern, and side sections, is assembled separately. Rivets and aluminum welding ensure durability. The frame consists of a keel beam running the length of the craft and transverse ribs providing rigidity. Aluminum rivets and specialized adhesive mixtures are used to connect sections, reducing weight. Large modules are lifted by powerful cranes and connected precisely using laser positioning to avoid errors. At the brightly illuminated shipyard, a giant module of the future craft rises into the air. A heavy gantry crane, weighing hundreds of tons, slowly lifts the aluminum section, gleaming in the sun like the shell of a marine predator. Metal cables are stretched tight like strings, while workers in protective helmets and vests carefully monitor every movement. The enormous part floats mid-air, gently swaying in the breeze. A crane operator, sitting high above the yard, maneuvers this colossus with extreme precision. Engineers below signal instructions, guiding the module to its exact position. When the section slowly settles into place, there's a dull metallic thud. Thousands of pounds of aluminum collide with the frame. Immediately, fastening begins. Workers tighten bolts, welding machines ignite with bright blue flames, and sparks scatter from beneath electrodes. The air fills with the scent of hot metal as the craft gradually takes shape, becoming a formidable combat machine. Engineers inspect structural integrity and tightness. Attachment points for the hovercraft skirt are installed on the frame. This system must be completely airtight to maintain LCAC stability during movement. The completed frame undergoes load and vibration tests. After passing successfully, engines, propellers, and electronics are installed. Now begins one of the most critical stages. The shipyard hums with crane motors, gently transporting massive gas turbine engines, the heart of the future craft. Workers dressed in protective suits and masks precisely position them in compartments, where every millimeter counts. Simultaneously, technicians attach enormous propellers, blades made from robust composite materials, which will later propel air with thousands of horsepower. When blades rotate for the first time, air waves ripple through the air, causing fabric on work uniforms to tremble. Inside, engineers connect cables, sensors, and onboard computers, carefully inspecting every chip, screen, and controller, as navigation, communication, and automated control depend on these systems. Once everything is ready, the moment of truth arrives. Pressing the first launch button, the massive frame shudders, turbines roar to life, and the first stream of hot air bursts from exhaust channels. The LCAC is ready for its first water test. A single modern LCAC costs from $50 to $75 million, depending on modifications. Operating costs are high due to gas turbine engines and demanding maintenance. Maintenance can occur at shipyards or specialized bases. Gas turbine engines require frequent service due to limited lifespans and costly repairs. The hovercraft skirt wears from contact with water, sand, and stones. Propellers and air systems require repairs as they operate continuously at high speeds. The United States is the leading producer of the new ship-to-shore connector crafts, replacing older LCACs. Great Britain builds similar crafts for civilian and military markets. Who uses them, you might ask? The United States Navy is the largest operator, possessing about 70 LCACs and acquiring new models. Japan uses LCACs for defense and humanitarian missions. Potential customers include NATO countries and nations expanding amphibious forces, like India and South Korea. Currently, LCACs are being upgraded to SSC, quieter, faster, and more efficient crafts. Demand is rising due to threats in the Pacific region and the need for rapid troop transport. Additionally, LCACs can drift. With the air cushion, they lack typical friction with water or land, allowing them to slide sideways, sharply change direction, and even pivot almost in place, making them exceptionally agile but challenging to control. LCACs use the same gas turbine engines as military aircraft, specifically the General Electric LM2500. Similar engines power F/A-18 Hornet fighters. Essentially, LCACs are aircraft that never leave the surface. Unlike conventional ships, they can move onto shore, cross sandy dunes, swamps, and even ice, providing advantages for landing troops in difficult locations. However, LCACs are among the loudest vessels in naval forces. Their noise can be heard hundreds of feet away, making them unsuitable for stealth missions. During operation, LCACs create powerful vortices, capable of literally blowing away seagulls and other marine birds, often making it impossible for them to remain airborne. Every single year, more than 170 million old refrigerators are disposed of throughout the world. However, what actually happens to them once they disappear from our kitchens? Refrigerants that can damage the ozone layer, hundreds of pounds of metal, plastic, and even precious metals all require specialized processing. Did you know that old refrigerators contain gold, silver, and copper that can all be given a second life? And some models are even sold to poorer countries instead of being recycled. Please stay with us to see how junk is turned into a resource and discover who is making millions of dollars in the process. In the United States of America, there are several ways old refrigerators are collected for disposal, ensuring safe and environmentally responsible recycling. Some large retail chains, such as Best Buy, offer programs to recycle old household appliances. When you purchase a new refrigerator, they can take the old one away for further recycling. These programs often come with restrictions, for example, no more than 3 appliances per day from a single household. There are a few reasons for limits on how many appliances can be recycled. The first reason is logistics and the burden on the system. since recycling centers have limited capacity. If everyone could drop off any number of appliances, the collection and recycling processes could become overloaded. These programs are also intended for individual consumers, not for businesses or resellers. The limits also prevent hauling companies from making free use of disposal services. The third reason concerns cost optimization. In many cases, recycling is subsidized by the government or by private companies. The restrictions help control expenses and distribute resources evenly. The final reason is environmental responsibility. These programs often encourage people to switch to energy-efficient devices rather than simply throwing away large quantities of appliances. It is a kind of balance between convenience for consumers and the operational efficiency of the recycling centers. In many cities and districts, there are municipal collection points for large household appliances. Consumers can bring their old refrigerators to these points, where specialized companies pick them up for recycling. These collection points can be stationary or mobile, which makes it more convenient for residents. Some energy companies also offer programs for disposing of old, inefficient refrigerators. They may provide financial incentives or free appliance removal to encourage consumers to switch to energy-saving models. There are also private companies that specialize in collecting and recycling large household appliances. They offer services to remove old refrigerators directly from the consumer's home for a certain fee. These methods of collecting old refrigerators support the responsible handling of electronic waste, ensuring proper recycling and minimizing negative impacts on the environment. After collection, old refrigerators are taken to specialized recycling centers, where they are sorted and prepared for disposal. This process unfolds in several main ways, which we will describe right now. Many major cities have specialized facilities that accept old appliances directly. For instance, in the United States of America, such facilities operate under programs focused on the responsible recycling of electronics. In some situations, refrigerators are first sent to warehouses or designated lots where enough units are accumulated for subsequent mass recycling. This saves on transportation costs and streamlines logistics. Some large brands, such as Whirlpool or LG, run their own recycling programs. They take back old refrigerators, break them down, and reuse some of the materials in the production of new appliances. Sometimes, old but still functioning refrigerators are sold or transferred to less developed countries. This practice is considered controversial because such equipment can consume a lot of energy and may contain hazardous substances. How do you feel about this issue? Is it better to have a refrigerator that poses potential harm, or is health more important than questionable humanitarian aid? In Europe, there are strict regulations regarding the recycling of household appliances. For instance, under the Waste Electrical and Electronic Equipment Program, refrigerators are transported to certified centers, where they are taken apart into environmentally safe components. At every stage of this process, safety regulations must be observed, because refrigerators contain refrigerants and other potentially harmful substances that cannot simply be dumped in a landfill. Before a refrigerator is sent for dismantling, its technical condition is assessed. Models that still work can be repaired and resold or donated to charitable organizations. Faulty or obsolete models are immediately directed to further processing. Next, refrigerators are categorized, since different models contain different materials and refrigerants. They are divided into industrial refrigerators, household refrigerators, and refrigerators containing harmful freon. After that, refrigerators are checked for the presence of hazardous gases and liquids. Freon and other refrigerants are removed because they require special disposal methods, as they deplete the ozone layer. Lubricants are drained, since they can contain heavy metals. Before extracting freon, technicians place the refrigerator in a designated treatment area, where they check which specific refrigerant is used. Technicians connect the refrigerator to a vacuum pump, which creates pressure inside the system and forces the freon to flow in the required direction. The refrigerant is drawn out through specialized valves, after which the gaseous freon is collected in sealed containers, while the liquid freon is filtered and can either be used again or sent for chemical recycling. The freon that is collected undergoes purification to remove oil, moisture, and metal particles. After that, it is either destroyed or reused in cooling equipment. Older banned refrigerants must not be released into the atmosphere, so they are incinerated in special high-temperature installations that break them down into harmless components, or they are converted into newer, safer gases through chemical reactions. All of this happens at certified facilities because mishandling Freon can cause damage to the environment. Once the Freon and other refrigerants have been dealt with, it is necessary to drain the lubricants from the refrigerator. These fluids contain pollutants that can harm the environment. The lubricant in a refrigerator is mostly in the compressor, which is responsible for circulating the refrigerant. During operation, it mixes with Freon, so removing both substances often occurs simultaneously, although it depends on the specific model. Before draining the lubricant, the compressor is removed or punctured so that the fluid can flow out freely. The lubricant then either drains by gravity into a collection tank, or it is pumped out by a vacuum device. Special containers are used to prevent spills and the evaporation of dangerous substances. The collected fluid is then purified of any remaining Freon, metal particles, and other impurities through settling and filtration. After purification, the lubricant can be reused in compressors if additional cleaning is performed. If it cannot be recycled, it is incinerated in special furnaces. It can also be applied in certain industries, for instance, in the production of technical lubricants. This is carried out at specialized facilities to prevent leaks of harmful substances into the environment. Modern refrigerators contain electronic boards, displays, and battery elements. Workers remove these parts by hand because automated conveyors cannot handle such components without damaging valuable materials. Prior to shredding, refrigerators undergo inspection. Wiring, plastic parts, and insulating panels are taken off. These materials are sorted for further recycling or safe disposal. In general, human oversight is required at every step to ensure safe and clean disassembly. However, certain processes are automated. For example, shredding metal housings or compressing plastics. The external body of a refrigerator is usually made of steel or aluminum sheet. It is separated either by hand or by hydraulic machines and sent for shredding. Compressors and condensers have a high content of non-ferrous metals, such as copper and aluminum, so they are taken apart separately. Copper and aluminum are then sent for smelting and used in new electric devices. Refrigerators also contain many plastic parts, such as internal panels, shelves, bins, and door gaskets. Workers remove these elements by hand because the plastic must be sorted by type. Certain types of plastic are recycled into pellets, which are later used to manufacture new products. Some refrigerator models feature glass shelves or glass doors in display-style refrigerators. This glass is removed manually, sorted by quality, and sent for remelting. Modern refrigerators include control boards, displays, wiring, and batteries. Electronic parts are taken out and transferred to specialized facilities for extracting precious metals like gold, silver, and palladium. Most refrigerators have foam polyurethane or polystyrene foam as insulation. It is removed or shredded, and some of that material can be used as filler in construction or for manufacturing new insulation. Metals go to metallurgical plants. Plastics are compressed into briquettes and sent to recycling facilities. First, the plastic parts, meaning bins, shelves, and outer components, are placed into special shredders. Inside these machines, blades or rotary cutters chop the plastic into tiny pieces no more than 2 inches in size. Next, the plastic fragments are washed in water baths to remove dust, adhesive residue, labels, and other impurities. Some plastics undergo separation, during which they are divided by density. For example, lighter polymers float to the surface, while heavier ones sink to the bottom. The cleaned plastic is sent through powerful drying units to ensure it has no excess moisture, since moisture can reduce the quality of the recycling process. The dried plastic is then fed into hydraulic or mechanical presses, where it is compacted under pressures of up to a few hundred short tons. This process occurs without heating, so the material does not melt but simply becomes more dense. The pressed plastic is formed into briquettes weighing from a few pounds to a few dozen pounds, depending on what clients need. The finished briquettes are wrapped in film or secured with metal straps so that they do not fall apart during transport. They are then shipped to factories, where the plastic will be melted and converted into new items, such as plastic containers, furniture, pipes, or even parts for new refrigerators. This method conserves space during transport and reduces logistics costs, since pressed plastic occupies several times less volume than loose fragments. Glass is remelted and used in new glass products. Electronic parts are recycled separately, and precious metals are extracted from them. Insulation materials are partly disposed of or reused. Thanks to modern technology, most materials from old refrigerators get a second chance at life. Every year, more than 12 million cars are scrapped worldwide, and this has become a massive industry running like clockwork. Imagine this. Your old ride could turn into a brand new skyscraper, and that worn-out engine might end up in a military battleship. But what actually happens to cars that have reached the end of the road? They are not simply tossed away. 90% of their materials get recycled. How are cars dismantled, crushed, and literally torn apart to be turned into something new? Today, we are taking a deep dive into this process. Why can you not just leave your old car sitting in the backyard? Well, first of all, it is illegal. Unless you live somewhere where keeping a car on bricks in your yard is completely fine. Second, old cars leak fluids, motor oil, antifreeze, transmission fluid, that can seriously damage the environment. Third, they take up space that could be used for something better, like a new car or even a barbecue grill. So, what are your options? If your car is still somewhat functional, you can sell it for parts. Even if the engine is done for, many components still have value. The battery, if it is still working, can be sold separately or taken to a recycling center. Tires, if the tread is still decent, can be resold. The catalytic converter contains precious metals like platinum, palladium, and rhodium, making it highly valuable. Headlights, mirrors, doors, there is always someone looking for replacement parts. You can sell them on Facebook Marketplace, Craigslist, or local auto shops that buy used parts. If your car is so far gone that even a tow truck refuses to take it, scrapping it for metal is the way to go. On average, scrap metal prices range from $100 to $300 per 2,000 pounds, meaning a regular sedan could get you anywhere from $200 to $600. Before dropping it off, make sure you have the proper paperwork, remove all personal belongings from the interior, and if possible, drain the fluids. Many scrapyards will pick up the car themselves, especially if it is undrivable. How about donating it to charity? In the United States, plenty of organizations accept cars as donations, even if they are not running. Some examples include Cars for Kids, Goodwill car donations, and Wheels for Wishes. You just make a call, they tow it away, and you get a tax deduction. Plus, it feels good knowing your old clunker is helping someone in need. From time to time, government programs allow you to trade in an old vehicle for compensation. In California, for instance, the Consumer Assistance Program offers up to $1,500 for cars that fail to meet environmental standards. It is worth checking if similar programs exist in your state because this might be the most profitable option. Do not leave your car abandoned on the street. That could result in fines or impoundment. Do not try to dismantle it yourself unless you know what you are doing. Some parts, like the fuel tank or battery, can be hazardous. And do not confuse proper recycling with illegal sales. Many states have strict regulations about selling non-operational vehicles without the right documentation. The key is doing it correctly to avoid trouble and protect the environment. In movies, we often see massive junkyards filled with rusting cars under the scorching sun. In reality, most vehicles do not just sit there. Modern recycling is a well-organized process where nearly 90% of materials get repurposed. If a car is beyond repair, it moves on to the dismantling stage. You already know about the initial teardown. After that, the car goes into a hydraulic press, the same machine you have probably seen in movies. It compresses the car into a compact cube, reducing its size by several times. These crushed cars are then sent to massive industrial shredders, huge machines that literally rip the car apart. After that, the shredded metal and plastic move on to sorting. Sorting is done using magnetic separators, which separate metals. Steel and iron are the easiest to extract since they are attracted to magnets. Aluminum, copper, and brass are removed using eddy currents and other techniques. Plastics, glass, and rubber are collected separately, although not everything can be recycled. Once sorted, the materials go to specialized recycling plants. Steel and aluminum are melted down and used to manufacture new cars, construction materials, household appliances, and more. Wheel rims and engine blocks are often turned into new auto parts. Components like bumpers, dashboards, and interior panels are shredded and reused for making furniture, insulation, or even new cars. Automotive glass contains a plastic layer inside, making it harder to recycle, but some companies repurpose it into construction materials. Tires do not decompose and are an environmental hazard, so they are repurposed as much as possible. They are turned into asphalt granules, rubber flooring for playgrounds, and even fuel for cement plants. 99% of car batteries are recycled. The lead is melted down, and the acid is either neutralized or reused. Despite all these processes, about 10 to 20% of car waste remains non-recyclable. This includes certain plastics, adhesive materials in upholstery, and textile or leather interior elements. Researchers are working on new disposal methods, such as pyrolysis, breaking materials down at high temperatures without oxygen, or using biodegradable materials for future vehicles. Today, around 12 million cars are recycled in the United States every year, making it one of the most advanced recycling industries. But back when cars first started taking over the roads, nobody really thought about what to do with them once they stopped working. Picture the early 20th century. Ford releases the legendary Model T. Cars become affordable to the masses, but what happens when they break down? In the early 1900s, old cars were often just left on the roadside or dumped in forests. Many were abandoned in backyards, slowly swallowed by weeds. Some cities even tossed them into rivers or burned them, simply because there was no system in place. Over time, scrapyards emerged, where enterprising individuals collected metal from wrecked cars, melted it down, and repurposed it. By the 1920s and 30s, metal was in high demand for construction, turning old cars into valuable resources. During World War II, the United States and Europe faced an enormous need for steel and other metals. Suddenly, junk cars became a gold mine. Governments even encouraged citizens to turn in their abandoned vehicles for scrap to produce tanks, weapons, and military equipment. By the end of the war, car recycling had become a structured industry, and businesses started opening specialized vehicle recycling plants. In the 1950s and 60s, cars became more affordable. People bought them in droves, and just as quickly discarded old models. Huge car graveyards emerged, where vehicles simply rusted away, taking up massive amounts of space. Soon, environmentalists raised concerns: oil leaks, gasoline spills, lead contamination — gasoline still contained lead back then — and other toxins were polluting the land and water. This pushed governments worldwide to implement stricter recycling regulations. By the 1970s, the first serious car recycling programs were introduced. Since the 1980s, vehicle recycling has become more systematized. Companies started using automated shredders to rapidly dismantle cars. Today, modern cars are about 80% recyclable, but manufacturers are working to push that number up by another 10%. In Japan and Europe, laws require automakers to take back their old models for recycling, encouraging the production of more eco-friendly vehicles. Recycling metal from old cars saves up to 74% of the energy compared to producing new metal. Some countries have extremely strict environmental standards: Germany, Switzerland, and Japan. In these places, before cars are crushed, they are burned in specialized facilities to remove plastic residues and other combustible materials. Sounds interesting? Absolutely. This process, called pyrolysis, happens in industrial furnaces designed for thermal decomposition. Once the vehicle fluids are drained and key components are removed, the car is placed in a high-temperature chamber. The temperature inside ranges from 800 to 1,200 degrees Fahrenheit. Materials break down without oxygen, causing plastics, adhesives, textiles, and other organic materials to evaporate, leaving behind only the metal frame. The gaseous byproducts go through advanced filtration systems to capture heavy metals and toxic compounds. The result: minimal emissions and a cleaned-out metal shell, ready for crushing or smelting. Every single year, the world's oceans are left with hundreds of gigantic liners that used to be floating cities. Imagine this. Only one specialized shipyard in the country of India dismantles over 400 ships per year, and the utilization of just one cruise liner can yield up to about 44,000 short tons of steel. How does a vessel that once cost billions of dollars turn into a heap of scrap metal? Who makes money on this process? And why do the majority of ships finish their journey in Southern Asia? Let us examine this process from the very first blueprint all the way to the very last cutting of the hull. Private yachts are produced all over the world, including in the United Kingdom, the Netherlands, Italy, and Turkey. But the major cruise liner production hubs are located in France, Germany, Italy, and Finland, where industry giants such as Chantier de l'Atlantique, Meyer Werft, and Fincantieri operate. Everything begins with the creation of a project, during which engineers and designers develop the overall structure, choose materials, and determine the technical specifications of the vessel. The design phase can last anywhere from 6 months to 5 years. Once it is approved, the shipyard begins manufacturing the main metal sections of the hull, which are later joined together in a massive dry dock or a specialized construction hangar. Construction starts with the production of large steel or aluminum sections that will form the hull. First, enormous sheets of metal are cut using laser or plasma cutting, and then they are joined by welding to create separate blocks. Each block can weigh anywhere from about 55 short tons to about 330 short tons, and their total number may reach into the hundreds, depending on the ship's size. After the welding is completed, the sections are painted with anti-corrosion coating and moved into a massive assembly dock, where the hull begins to take shape. The assembly process involves powerful cranes that lift the blocks and connect them to one another. Once the main structure is finished, the hull is reinforced with internal bulkheads, and initial communications are installed, including piping systems, ventilation ducts, and electrical cables. When the hull is fully assembled, it is launched into the water, and the fitting out of the interior begins. Partitions, electrical grids, heating and ventilation systems, air conditioning, and safety systems are put in place. At this stage, the ship gradually starts to look the way it will when it is completed. First, special soundproofing and thermal insulation materials are applied to the ship's metal hull, because the liner must be not only strong, but also comfortable. Next, metal frameworks are installed to serve as the foundation for the partitions and other structures. These frames are made of lightweight materials, such as aluminum or composite panels, to keep the vessel's overall weight lower. Thanks to modular technology, large sections of cabins and public areas are assembled at separate production facilities and then transported to the liner, where they are rapidly installed. Passenger cabins are usually manufactured as complete blocks, each including walls, flooring, plumbing, and furniture. These blocks are then transported to the ship and placed in their designated spots, after which they are connected to the ship's electrical network and water supply and ventilation systems. Larger liners can have more than 2,000 of these modules, and installing them can take several months. Public areas are much more complex, since each restaurant, theater, or lobby has its own design and intricate architectural solutions. For example, theater stages are equipped with moving platforms, sound systems, and lighting that is integrated into the ceiling. Swimming pools receive water purification systems, and sports courts are fitted with special non-slip surfaces designed to withstand wave movement. During the final stage, furniture, decorative panels, lighting, and finishing touches are installed. High-quality materials are used, ranging from exotic woods and marble to stained glass. Designers pay attention to every single detail in order to create an atmosphere of luxury and comfort. Once construction is complete, all systems undergo meticulous testing, including elevators, ventilation, safety features, and communication lines, so that the liner is fully prepared to welcome passengers. At the same time, powerful engines and control systems are installed on board. The main engines, which are typically diesel or hybrid, are mounted in the engine room before the liner's hull is completely enclosed. Each engine can weigh anywhere from about 22 short tons to about 55 short tons, and there may be between 3 and 6 engines depending on the ship's size. They are delivered to the shipyard dock by specialized cranes, then lowered through the engine room's top hatch and attached to vibration-damping mounts that reduce noise and vibration during operation. After the engines have been installed, drive shafts are added to transmit rotational motion to the propellers, or, in the case of electric motors, they are connected to the power supply system. Most modern liners use azipod units, which are powerful electric motors capable of rotating around their own axis, giving the ship excellent maneuverability. All power units are connected to control systems located on the bridge and in the engine room. Once every technical system is in place, the liner is readied for its initial tests. First, static tests are conducted while the ship is still in the dock, checking how the engines function without leaving port. The power units are started up, and the electrical supply, fuel pumps, cooling systems, and emergency mechanisms are tested. Computerized control systems, which manage navigation, automatic speed adjustment, and ship stability, are also checked at this stage. Following these static tests, the liner is launched for sea trials, which last from about 2 weeks to about 6 weeks and include checking speed, maneuverability, and the operation of all systems under real-world conditions. The captain and technical personnel test how the vessel responds to commands, examining braking efficiency and the performance of the stabilization systems. The liner is taken into open waters, where the engines are tested at maximum power. Fuel consumption is measured, and noise and vibration levels in cabins and public areas are evaluated. In the final phase of testing, safety systems are examined by simulating emergency scenarios, testing firefighting systems, lifeboats, evacuation routes, and communication with shore-based services. Only after all tests are successfully completed is the liner formally handed over to the client, and it sets sail on its maiden voyage. But sooner or later, every liner heads out on its last voyage. Since no technology lasts forever, what happens to yachts and other vessels afterward? Are they actually utilized? And if so, how? According to data from the International Maritime Organization, around 1,000 seagoing vessels are utilized each year, of which about 200 are large cruise liners and passenger ships. Most of these vessels are dismantled in South Asian countries such as India, Bangladesh, and Pakistan, where the world's largest ship utilization shipyards are located. For instance, in the city of Alang in India, there is one of the biggest shipyards, which processes over 400 ships per year. First, the ship's owner assesses the condition of the liner and compiles a list of materials that can be recycled, sold, or require specialized disposal. The utilization of a single large cruise liner can produce up to about 44,000 short tons of steel, which, after recycling, is used in construction and other industries. In addition to metals, other materials such as wood, glass, and plastic are removed from the vessels for recycling or safe disposal. During this period, the ship heads to the specialized shipyard that handles the disassembly of ships. The largest of these facilities are located in India, Bangladesh, Turkey, and Pakistan. The liner or yacht makes its way to the site for utilization under its own power, or is towed if its engines are no longer functional. When the vessel arrives at the shipyard, the preparatory work begins. A team of engineers and environmental specialists evaluates the potential risks connected to hazardous substances, including fuel, lubricants, coolants, chemicals, asbestos, and lead. All of these materials must be carefully removed to prevent environmental contamination and to protect the workers' safety. In the first step, any remaining diesel fuel is pumped out of the tanks, which can amount to anywhere between about 10 short tons and about 55 short tons, depending on the size of the vessel. Next, the pipelines, oil filters, and engine cooling systems are cleaned to remove all residual lubricants and chemicals. Specialists also deal with air conditioning and firefighting systems, which might contain harmful gases like freon. After that, the ship is disconnected from all power, the electrical networks are shut down, and the batteries containing toxic substances are removed. In the engine room, the generators are dismantled. They can be resold or used on other ships. During this period, specialists also check for hazardous materials, such as asbestos, which was once used for pipe and wall insulation. Asbestos is carefully taken out, sealed, and delivered to specialized facilities for safe disposal. The next step involves removing all equipment and items that might be reused or sold. Furniture, lighting fixtures, plumbing, doors, decorative panels, carpets, and even kitchen appliances are dismantled from the liner. Many of these items are sold on the secondary market or used on other vessels and in hotels. The following stage is dismantling. First, the ship is secured in a dry dock or pulled onto a specially designated beach, which is common in South Asian countries such as India or Bangladesh. This stabilization is necessary to keep the hull steady during cutting because losing balance could cause an accident. Next, the upper structures are gradually taken apart, including the top decks, bridge, funnels, and other external components. These sections are typically removed in large pieces using cranes. Workers start dismantling the upper structures and decks, steadily moving down toward the main hull. Metal parts like steel and aluminum are cut into smaller segments, and the separated materials are sorted and prepared for subsequent recycling. For example, steel is melted down to create new products, while non-ferrous metals such as copper and aluminum are put to use in various industries. When the upper structures have been fully removed, the main hull is cut apart. Several methods can be used, depending on the thickness of the steel and where the ship is located. The most widespread method is gas cutting, where specialized torches heat the metal to over 1,500 degrees Celsius, which is about 2,732 degrees Fahrenheit, and then the steel is sliced by a stream of oxygen. For thicker steel sections, which can be up to about 8 inches thick, plasma cutting or hydraulic shears may be used. Cutting of the hull begins from the top and proceeds downward so that the structure does not collapse under its own weight. Huge steel blocks, weighing anywhere from about 55 short tons to about 110 short tons, are separated and moved to specialized areas, where they are further broken down for recycling. On average, the hull of one large cruise liner can yield from about 33,000 short tons to about 44,000 short tons of steel, which is later reused in construction and shipbuilding. Special attention is paid to cutting the underwater part of the hull, since it is the sturdiest section and contains ballast tanks that might hold residual water. Underwater welding and cutting techniques are employed if part of the hull remains in the water at that stage. In the final phase of dismantling, the last remains of the keel and bottom are cut into fragments, which are loaded onto trucks or barges for transport to metallurgical plants. Utilization of cruise liners and yachts can last from a few months to more than 1 year, depending on the vessel's size and construction. Completing the dismantling process signifies that the ship officially ceases to exist. All materials suitable for reuse are sent for recycling, and everything else that cannot be repurposed is disposed of in accordance with environmental regulations. It is important to note that the utilization process must meet international environmental standards. Organizations such as the International Maritime Organization develop guidelines and standards for the environmentally sound utilization of ships, known as the Hong Kong International Convention for the Safe and Environmentally Sound Recycling of Ships. Every single year, more than 20 million short tons of dairy products are produced worldwide, and Nestlé condensed milk takes a significant portion of that total. Just imagine this. Each day, over 100,000 gallons of milk arrive at the company's factories, but even the freshest milk still shows up dirty. Yes, indeed, microscopic particles of dust, feed, and even traces of blood can make their way inside. How do they turn all that into perfectly smooth, thick condensed milk that melts in your mouth? And why would it be a completely different product without those tiny lactose crystals? Watch until the very end. You will not believe what every drop goes through. Today, Nestlé is one of the leading global companies in the food industry, and its products, including condensed milk, are represented in many markets around the world. It all started in the year 1866, when the Anglo-Swiss Condensed Milk Company was founded, becoming the very first to produce condensed milk in Europe. Meanwhile, in the year 1867, the Swiss pharmacist Henri Nestlé developed the first infant milk formula, which marked the beginning of the Nestlé brand. Nestlé began producing condensed milk in the 1870s, entering into direct competition with Anglo-Swiss. However, in the year 1905, the two companies united, forming one large corporation called Nestlé, and Anglo-Swiss Condensed Milk Company. This move provided the impetus for rapid development of condensed milk production and export all over the world. Initially, condensed milk was positioned as a nutritious and long-lasting product that could replace fresh milk, especially in regions with limited access to high-quality dairy. Because of its prolonged shelf life and ease of transportation, it quickly gained popularity, not only among military personnel and travelers, but also in everyday family life. In the United States of America, Nestlé began its active condensed milk production at the start of the 20th century, constructing its factories and expanding its market presence. Over time, the brand came to be associated with high quality, and Nestlé condensed milk became an integral part of culinary culture, especially in desserts, baked goods, and coffee beverages. Today, Nestlé continues to produce condensed milk under different brand names, supplying markets in the United States of America and worldwide with products that combine tradition and modern standards of quality. The milk that is delivered to Nestlé factories is subject to extremely strict requirements. The company adheres to international quality and safety standards to guarantee the production of flawless products. Milk is supplied from verified dairy farms, where cows receive balanced nutrition and veterinary care. Before being sent to the factory, the milk undergoes its initial quality tests right there on the farm. The level of fat, protein, and the absence of antibiotics or other unwanted impurities are checked. Milk is transported in special refrigerated stainless steel tanks. The temperature during transportation is maintained at approximately 39 degrees Fahrenheit to preserve freshness and prevent bacterial growth. These tanks are sealed and regularly disinfected to ensure the highest standards of hygiene are upheld. Every day, around 100,000 gallons of milk arrive at Nestlé factories. Once the milk reaches the factory, it is tested again in the laboratory. Only then does it go into the main production process. The milk that makes the cut is fresh, safe, and of the finest quality. Precisely what becomes the foundation for the legendary Nestlé condensed milk. But how does it become so exceptional? An interesting fact is that no matter how perfect the process might be, the milk inevitably arrives at the factory dirty. As surprising as it may sound, the milk can contain microscopic particles that end up there during milking or transportation. These may be small leftovers of feed, dust, tiny bits of dirt from milking equipment, or other undesirable elements that are invisible to the naked eye. It is totally normal, since milk is a natural product, and these microscopic contaminants may appear during milking or storage. Cleaning and filtration are essential steps at the factory, which make the milk cleaner and safer for consumption by removing such particles. After the milk arrives, it first passes through filters that trap larger particles like hair, bits of feed, dust, or any other visible impurities. This is the primary step in getting rid of coarse debris. Next, the milk may go through a centrifuge. During this process, the milk spins at high speed, and due to centrifugal force, heavier particles like fat, impurities, or even traces of blood that might have entered the milk during milking are separated. You might wonder where blood could come from. I will explain. In a cow's body, blood is what transforms into milk in a complex biological process. Plus, an animal can have minor scrapes. Centrifugation also allows for standardizing the milk's fat content, if necessary, depending on whether high-fat or low-fat milk is being produced. The next phase is microfiltration. This is a finer filtration method that uses special membranes to remove small particles and microorganisms. It helps ensure even greater purity of the milk, which is crucial for the safety of the final product. After filtration, the milk is cooled to a low temperature, around 40 degrees Fahrenheit, to maintain freshness until further processing steps, such as pasteurization. Initially, the cleaned and cooled milk is temporarily stored in large, sterile stainless steel tanks. The pasteurization process at large factories like Nestlé is fully automated. When pasteurization begins, the milk flows from the tanks to the pasteurization units through sealed pipes. These pipes are made of stainless steel, which eliminates the possibility of contaminating the milk during transfer. Before entering the pasteurization apparatus, the milk may once again pass through filters for additional removal of any small particles that might still be present. The milk is pumped through the system by pumps that regulate both pressure and flow rate, ensuring a smooth, continuous process. The milk goes directly into a plate or tubular heat exchanger, which is a specialized piece of equipment that rapidly raises the milk to the necessary pasteurization temperature. The tubes or plates are heated by hot water or steam, and as the milk passes through them, it is heated to the required temperature, for example around 167 degrees Fahrenheit. In enormous silver-colored stainless steel tanks that resemble giant gleaming columns, fresh pasteurized milk is stored. Through a network of intertwining pipes, which seem almost like steel veins, the milk travels to separators, machines that rotate at extremely high speed, creating a fascinating visual effect. Inside these machines, the milk is separated into cream and skim milk under the influence of tremendous centrifugal force, which is difficult even to imagine. The large storage tanks at factories like Nestlé can hold anywhere from 5,000 to 50,000 gallons of milk, depending on the scale of production. The most common tanks have a capacity of about 30,000 gallons. On special display screens, digital readouts show the fat content, density, and temperature. Everything is under strict control. Robotic arms measure the exact amount of cream, blending it with skim milk to achieve the perfect balance. This step is reminiscent of how an artist carefully selects just the right shades of paint for a canvas. This is milk standardization. The process is automated and appears almost futuristic. Pipes carrying the milk, immaculate cleanliness, the hum of high-speed machines, and precision down to the thousandths of an ounce. The standardized milk comes out of the system, prepared for the next steps. To make sweet condensed milk, they add sugar, which can be around 40 or 45% of the mixture. Sugar here does more than just sweeten. It also acts as a preservative, helping the product last longer. The primary stage is removing excess water. The milk and sugar mixture is fed into vacuum evaporation systems, where, under reduced pressure, the blend is heated to approximately 150 degrees Fahrenheit. Thanks to the vacuum, the water evaporates quickly without scorching the milk. The outcome is a thicker mass with a significantly lower water content, about 30% instead of 87%, which is found in ordinary milk. After evaporation, this milk mass is still very hot and extremely thick. It is transferred to special cooling tanks, where cold water or a cooling fluid circulates along the walls. These are huge metal containers through which a chill seeps, almost like a gentle winter breeze. Large paddles, similar to giant mixers, slowly stir the milk, turning smoothly and steadily, so the mass does not settle or stick to the walls. The process is slightly like making ice cream. The hot mixture gradually cools down to about 90 degrees Fahrenheit. When the temperature reaches the right point, lactose crystals, milk sugar, are introduced into the mixture. These tiny, almost imperceptible particles act as seeds for the formation of thousands upon thousands of microscopic crystals in the milk mass. The milk continues to be gently stirred, and the crystals begin to grow in a very uniform way, thanks to precise temperature control and carefully managed stirring speed. If this process is disrupted, the crystals become too large, and then the condensed milk would end up grainy rather than smooth and creamy in texture. At the end of this process, the condensed milk attains the smooth, thick consistency, with a slight sheen that we all recognize. The result of perfect cooling and the meticulous handling of lactose crystals. In this way, from the chaotic ocean of hot milk emerges the sweet and tender product we know as condensed milk. Before packaging, the condensed milk is filtered one more time to remove any possible remaining unwanted particles and is tested for compliance with the standards. The finished condensed milk is packaged into cans, tubes, or pouches in aseptic conditions, sealed tightly, and then sent for cooling. Afterward, the product is ready for storage and distribution. Every single day, more than 20 million banknotes are destroyed in the United States. That is a mountain of money that could reach the sky. But what exactly happens to them? Are they burned? Shredded? or maybe turned into something completely unexpected. US dollars have their own life cycle, and their disposal is a high-security operation involving armored trucks, strict inspections, and secret routes. How do old banknotes disappear forever? And is there any way to save them? Let's find out. The dollar as a currency has a fascinating history. It all began in the mid-17th century. The first dollars appeared in the New England colonies in the year 1690, at a time when the United States did not yet have a unified national currency. Back then, the colonies issued their own money, and one of these was the so-called paper dollar. However, the true dollar as we know it today emerged later, in the year 1792, when the United States Congress passed the Coinage Act. This was the country's first attempt to introduce a single currency, establishing the dollar standard based on a silver coin. The dollar quickly became the main currency for trade and wealth accumulation, as the nation sought to create a stable and accessible monetary system that would support its economy and commercial ties. Today, the dollar has evolved into one of the world's leading currencies, used in international transactions across the globe. The idea of disposing of old banknotes arose at the beginning of modern financial systems, especially when currencies started to become standardized and central banks began managing the money supply. In other words, the process of removing worn-out dollars started as soon as money became a stable and regulated instrument, though it was not officially systematized until much later. The concept of destroying damaged money first appeared in Great Britain during the 19th century, when the British government realized that allowing worn-out banknotes or coins to remain in circulation reduced the overall value of the currency. However, the systematic destruction of money, as it is done today, only became possible with advancements in modern financial systems and technology. In the United States, the first efforts to manage old and worn-out dollars began in the mid-19th century, when the first central authorities responsible for currency emerged, and money became a key instrument of the national economy. In the year 1861, when the United States first introduced federal paper money, known as greenbacks, the need arose to organize their circulation, including their disposal. The official process of destroying old dollars was established by the Federal Reserve after its creation in the year 1913. The Federal Reserve became the primary institution responsible for regulating the money supply, including removing old banknotes from circulation. The idea of destroying old banknotes was first introduced by central banks, which discovered that worn-out and damaged money not only harmed the image of a national currency, but could also create economic problems. If old banknotes remained in circulation, it could destabilize the monetary system, increase the risk of counterfeiting, and even affect inflation rates. To prevent this, the Federal Reserve established a clear policy outlining when and how banknotes should be removed from circulation. This became an essential part of maintaining economic stability. So, what exactly happens to all the money that can no longer be used and that no one wants to see anymore? Are they just burned? Well, not exactly. Disposing of US dollars is a complex process that follows a highly regulated system, ensuring both destruction and security. Here's how it works. First of all, when money is removed from circulation, whether it is declared damaged or obsolete, it does not simply get thrown in the trash. Everything goes through the United States Federal Reserve System, which manages the issuance and renewal of dollars. They collect old banknotes and send them to specialized facilities for further disposal. When you or someone else brings damaged or worn-out dollars to a bank, that is where the process begins. Banks have strict procedures for identifying banknotes that are no longer fit for circulation. These banknotes are inspected both manually and automatically using specialized machines that detect damage, wear, or counterfeit signs. Modern ATMs and cash dispensers are also equipped with sensors to detect worn-out banknotes. If a bill is found to be damaged or degraded, it is usually placed into special compartments or sent to sorting machines in banks. Once a sufficient number of old banknotes accumulate in banks, they are sent to the next stage, the Federal Reserve. These are special facilities located across the country that inspect, replace, and dispose of currency. Several such centers exist across the United States, strategically positioned to efficiently serve all regions. The process of transporting old banknotes to the Federal Reserve or specialized disposal facilities is strictly regulated. Banks typically work with security firms specializing in transporting large sums of money. Old banknotes are packed into special bags or containers that are sealed and secured against unauthorized access. This is crucial because even old money remains a potential target for theft or counterfeiting if not handled properly. Security guards or specialized couriers deliver these packages to the Federal Reserve or disposal facilities. The transport companies involved in this process operate under the highest security standards, and shipments are often escorted by police or other security services when necessary. You would not believe how many old banknotes accumulate each year, and this applies not only to US dollars, but also to other currencies. Bank vaults are not limitless in space, so from time to time, large batches of worn-out bills must be removed. Every day, thousands of banknotes pass through people's hands. Some get crumpled, some get coffee spilled on them, and some even end up in the laundry. Add the natural wear and tear, and you have a massive pile of money that is no longer usable. Imagine this: every single day, the United States Federal Reserve destroys millions of banknotes. If you stacked them up, they would reach as high as a skyscraper. And that is just in one day. Transporting such massive amounts requires trucks. Money is packed into special bags or boxes. Each container has a unique number and seal to ensure it remains unopened. And while these may no longer be real money in a traditional sense, they still hold value. So the security of such shipments is incredibly tight. It is almost like a scene from an action movie. Armored trucks, armed guards, secret routes. Except here, instead of a heist, the mission is to get rid of this money forever. A true financial thriller, right? Before the old banknotes are destroyed, they go through careful inspection. Special systems determine whether they can be reused. If a banknote still retains at least 50% of its original form, it can be reintroduced into circulation after a special treatment, such as reprocessing or trimming. This significantly reduces the cost of printing new banknotes. Every year, an enormous amount of old dollars is destroyed in the United States. For example, in the year 2020, around 7 billion banknotes were eliminated because they were too worn out to remain in circulation. This process is continuously maintained at the highest level to keep the currency stable. Some damaged banknotes are not immediately burned. Instead, they are recycled into other materials, such as fibers that are later used to produce new banknotes. This helps reduce production costs and support sustainability efforts. There is also an interesting psychological aspect to this process. For many people, destroying money might seem like a loss of value, but in reality, it is part of a continuous cycle that helps preserve the stability and worth of the currency. That is why this process is just as crucial as printing new money. Old US dollars are often destroyed in specialized incinerators or through processes that ensure maximum material utilization. Banknotes are burned at temperatures of approximately 2,000 degrees Fahrenheit, completely obliterating them. Furthermore, advanced filtration and technology capture toxic gases and other harmful byproducts to ensure safety during the process. But does it not feel strange to burn so much money? Given how much we spend daily, these sums seem enormous. However, the portion of money that gets destroyed is actually a tiny fraction of the total circulating supply. In the end, the system is highly reliable and efficient. After the banknotes are burned, tons of ash remain. Some companies repurpose this ash into materials for making compost or even bricks. This part fascinates me. Dollars get reborn and continue serving humanity in new ways. Every single day, airplanes across the world consume more than 5 million barrels of aviation fuel. This fuel is the lifeblood of aviation. Without it, not a single jetliner would take off. But have you ever wondered how it is made? From oil refineries to the ultra-pure tanks inside aircraft, the journey of jet fuel is packed with chemical secrets, strict regulations, and even technologies originally developed for military fighter jets. Today, we are pulling back the curtain on this fascinating process and uncovering all its secrets. Jet fuel is a crucial component of the aviation industry. It must meet stringent quality standards to ensure the stable operation of both turbojet and turboprop engines. The primary source for jet fuel production is crude oil, which undergoes a complex technological journey from extraction to the final product. It was obtained through the distillation of crude oil. In the year 1903, the Wright brothers made the first controlled flight with the Wright Flyer, powered by a gasoline engine. In the early days of aviation, gasoline remained the primary fuel, as piston aircraft engines required a high degree of fuel volatility. However, during the 1920s and 1930s, engineers began considering kerosene as an alternative to gasoline due to its higher energy density, making it more suitable for high-altitude flights. German engineer Hans von Ohain and British designer Frank Whittle independently developed the first operational jet engines. Can you believe it? It is true what they say. Ideas are in the air. So, in the year 1939, Germany tested the first jet aircraft, the Heinkel He 178, which ran on specially refined kerosene. In the year 1941, Britain responded to the Nazis by launching the Gloucester E into production, the first British jet aircraft. Around the same time, engineers began developing special types of kerosene that met the demands of jet engines. Military nations involved in the war experimented with various fuel formulations to ensure high energy density, resistance to low temperatures, and low corrosiveness for fuel systems. During the war, jet fuel had a primitive composition, but over time, its standards improved significantly. After the devastating Second World War, jet aviation began rapidly advancing. This created a demand for improved fuel that could provide reliability at high altitudes, better thermal stability, and the absence of harmful impurities. In the 1950s, the first standardized types of jet fuel emerged. Let's take a look at them. JP1, developed in the year 1944, was an early standard for military aviation. JP4, introduced in the year 1950, was a blend of kerosene and gasoline that improved performance in cold temperatures. JP5, introduced in the year 1952, had a higher flash point and was used on US aircraft carriers. Commercial aviation also introduced its own standards, and in the 1950s, Jet A and Jet A1 were introduced as the primary fuels for commercial aircraft. With the development of supersonic aviation, such as the Concorde, and new generation military aircraft, the demand for higher quality fuel increased. Fuel now needed a lower freezing point, as flights took place at extremely high altitudes. This led to the introduction of anti-static and anti-corrosion additives, improving safety. Fuel systems were also designed to prevent icing, as jet fuel could cool down to -40 degrees Fahrenheit or lower. In the 1980s, the military adopted JP8, replacing JP4. This new standard contained fewer volatile components, making it safer to store and transport. The 1990s marked the beginning of the modern era of jet fuel production. So, let's move on to the steps involved in making jet fuel today, starting with crude oil extraction. Jet fuel is derived from hydrocarbons found in crude oil or natural gas. There are several methods for extracting crude oil. The first method is natural pressure extraction, where oil flows to the surface due to its own pressure. This is common in young oil fields. The second method is mechanical pumping, where pumps are used to lift the liquid to the surface. The third method is secondary recovery, where water or gas is injected into the reservoir to increase pressure and stimulate oil flow. Once extracted, crude oil contains impurities such as water, gases, and solid particles that must be removed before refining. Before transportation to the refinery, crude oil undergoes purification. First, water is separated using separators and chemical agents to remove emulsions. Next, degassing removes light gaseous hydrocarbons. Finally, filtration removes solid particles. In storage tanks, the flow slows down, allowing heavier particles to settle, while lighter fractions rise to the top. After this preparation, crude oil is transported to refineries through pipelines or by tanker ships. The next step is the separation of crude oil into different fractions. Let me explain how this process works. The process begins by heating crude oil to temperatures between 662 and 752 degrees Fahrenheit inside a massive distillation column. Through evaporation and condensation, we obtain different fractions: gaseous hydrocarbons, gasoline, kerosene, diesel fuel, and residual fuel oil. The gaseous hydrocarbons include methane, ethane, propane, and butane. The kerosene fraction serves as the primary raw material for jet fuel and undergoes further purification. To improve the quality of the kerosene fraction, it is treated to remove sulfur, nitrogen, and oxygen-containing compounds through hydroprocessing. This process occurs under pressures ranging from 30 to 80 atmospheres and at temperatures between 572 and 752 degrees Fahrenheit, using catalysts such as nickel molybdenum or cobalt molybdenum compounds. As a result, sulfur content is reduced, minimizing corrosion and harmful emissions. Additionally, fuel stability improves, allowing for longer storage without sediment formation. If crude oil does not contain enough kerosene fraction, catalytic cracking or hydrocracking is used to break heavier fractions into lighter ones. Catalytic cracking employs catalysts to break large molecules into smaller ones, while hydrocracking uses hydrogen to produce stable hydrocarbons. These processes help increase the yield of kerosene for jet fuel. After purification and modification, special additives are added to the kerosene fraction to enhance its properties. Antioxidants prevent sediment formation and maintain fuel system cleanliness. Anti-static additives reduce the risk of electrostatic charge buildup during refueling. Anti-corrosion agents protect fuel tanks from corrosion. Anti-freezing additives ensure stability at low temperatures. After additives are introduced, the fuel undergoes final filtration and preparation for distribution. To meet international standards, jet fuel undergoes strict quality testing. Viscosity determines fluidity at low temperatures. The freezing point for Jet A1 must not exceed -52.6 degrees Fahrenheit. The heat of combustion must be at least 18,400 British thermal units per pound. Water content must not exceed 0.46 0.02 of a grain. Electrical conductivity ensures safe refueling without sparks. If the fuel fails to meet standards, it is sent for reprocessing. And now, we reach the final stage of our journey. The finished jet fuel is stored in tanks with moisture and temperature protection. It is transported primarily through pipelines to airports. Large volumes are shipped by rail tankers. Tanker ships handle international deliveries. Trucks deliver fuel to remote airports. During transportation, it is crucial to prevent contamination with water or foreign substances that could compromise fuel quality. By the year 2025, the United States is projected to consume nearly 2 million barrels of aviation fuel per day, totaling approximately 86 million tons per year. As one of the world's largest consumers of jet fuel, the global demand is expected to be significantly higher. The aviation industry is actively working on developing renewable jet fuels to reduce greenhouse gas emissions and improve sustainability. With advancements in technology and environmental regulations, the future will see wider use of biofuels and synthetic alternatives, making aviation more eco-friendly. And most importantly, jet fuel keeps airplanes flying. The next time you board a plane for a vacation or business trip, remember the complex production process that brought that fuel to the aircraft. I think it is worth it. What do you think? Every year, over 150 million carats of diamonds are mined worldwide. But did you know that some mines are so deep that the temperature inside exceeds 110 degrees Fahrenheit, and powerful explosions can cause seismic tremors felt up to 50 miles away? Diamond mining isn't just digging. It's a full-scale scientific operation that starts with satellite analysis and can last for decades. How are these precious stones found? How do drilling rigs reach depths of 10,000 feet? And what happens to diamonds after they're mined? Let's break it down together. Diamonds form deep beneath the Earth's surface and are brought up through volcanic processes that create kimberlite pipes. These pipes, made of ancient igneous rock, are the primary sources of diamonds and can reach depths of over 10,000 feet, with temperatures inside the mines exceeding 110 degrees Fahrenheit. To cool these environments, powerful ventilation systems compress air. In some mines, the air is so pressurized that if a door between compartments is suddenly opened, the wind force can knock a person off their feet. Sounds dangerous, right? Before mining begins, geologists conduct extensive exploration that can last for decades. The process starts with analyzing satellite images and aerial photography. This is followed by field studies, where geologists collect rock samples for chemical analysis. Special attention is given to the presence of indicator minerals like garnets, ilmenite, and pyrope, which suggest the potential presence of diamonds. If the exploration yields positive results, detailed surveying begins. Drilling rigs create boreholes up to 10,000 feet deep, extracting core samples, cylindrical sections of rock. These samples undergo thorough laboratory analysis to assess the diamond content in the rock. Geophysical methods like magnetic surveys, electromagnetic scanning, and gravimetry are used. Open pit mining is employed when the deposit is relatively close to the surface. Underground mining is used if diamond-bearing rocks are located at significant depths. Mine shafts are constructed, allowing workers and equipment to descend. Mining begins with drilling boreholes into the kimberlite rock. For this, massive drilling rigs over 50 feet tall are used. Each borehole can reach lengths of 2,000 feet, and a single mine may have tens of thousands of such holes. After drilling, explosives are placed in the boreholes, and the detonation occurs under strictly controlled conditions. Some diamond mines use such powerful explosives that underground blasts can trigger minor seismic tremors detectable over 50 miles away. First, vertical shafts are dug, reaching depths of over 10,000 feet. The diameter of the main mine shafts often exceeds 20 feet. Additionally, horizontal tunnels are constructed, stretching for several miles. After the explosion, the rock in the mine breaks into pieces of various sizes, from large boulders to fine gravel. Powerful loaders with buckets lift the debris and transport it to central transfer points. Here, massive dump trucks, each capable of carrying over 250 tons of rock, load the extracted material and deliver it to the main tunnels. In some mines, instead of trucks, specialized electric trains running on tracks tens of miles long are used, capable of transporting over 500 tons of kimberlite rock per trip. The main tunnels are equipped with conveyor systems that start at depths of several thousand feet and extend to the surface. The length of these belt conveyors can exceed 15 miles, with belt widths over 6 feet. Some systems have multi-level structures, allowing simultaneous material transport from different parts of the mine. Before being placed on the conveyor, large rock fragments pass through crushing stations, where massive steel rollers over 20 feet long break the debris into fragments no larger than 3 feet in diameter. The crushers operate with compressive forces of tens of thousands of pounds per square inch and can process over 10,000 tons per hour. After initial crushing, the material is loaded onto the main conveyor belts, which transport it to the washing system. In some sections, the conveyors pass through special grottos equipped with giant sieves with holes of various sizes. During transport, smaller rock particles are sifted and directed to separate processing lines, while larger pieces move to the next stage of crushing. The newest mines are equipped with automated control systems that analyze the rock composition in real time and adjust conveyor speed and crushing intensity. As the future diamonds approach the surface, they are fed into special bunkers where the rock accumulates, ready for further processing. The capacity of these bunkers can exceed 100,000 tons, and their structure allows for even material distribution to washing and sorting facilities. In mines located in deep regions, transporting the rock can take several hours, with annual extraction volumes reaching millions of tons. When I was a kid, my family loved going to the beach. It didn't happen often, my dad rarely had time off, but when it did, everyone was thrilled and happy. Diving underwater to find seashells, crabs, or even clams, I never imagined that diamonds could be mined from the sea. Deep sea diamond mining is one of the most complex and technologically advanced methods in the mining industry. Mines are located where kimberlite pipes or alluvial deposits lie beneath the ocean floor at depths exceeding 500 feet. Geologists begin by conducting surveys using underwater drilling rigs. These rigs are stationed on specialized offshore platforms or vessels equipped with computerized navigation systems for precise positioning over potential deposits. Once diamond-bearing deposits are confirmed, the construction of an underwater mine begins. This is a complex process involving the creation of sealed tunnels or the use of massive drilling capsules operating under high pressure. One method involves using giant seabed drilling complexes, which can exceed 200 feet in length and weigh over 5,000 tons. These complexes are equipped with diamond-tipped drills capable of cutting through even the hardest rock. During drilling, a specialized hydraulic system creates a water flow under pressures exceeding 3,000 pounds per square inch, washing out small rock particles and diamonds into special reservoirs. Another method uses giant underwater vacuum systems that can descend to depths of up to 1,000 feet and suck up hundreds of thousands of cubic feet of rock per hour. The material is then brought aboard a vessel or platform for initial processing. Special underwater crushers can process up to 50 tons of kimberlite rock per hour. Powerful pumping systems are used to transport the rock to the surface, capable of moving up to 1 million gallons of water per day. Streams of enriched rock are directed through pipelines that can stretch for several miles. The material then enters large sorting tanks, where it passes through gravity separators. Heavier diamonds settle at the bottom, while lighter particles are washed away and returned to the sea. Remotely operated underwater vehicles play a crucial role in deep-sea mining, operating at depths of up to 10,000 feet. They are equipped with manipulators that can precisely collect large diamonds directly from the seabed. Their high-resolution cameras allow operators, located hundreds of miles away, to control the process in real time. Deep-sea mining is so complex and costly that only a few countries in the world have the necessary technology. It can cost hundreds of millions of dollars, and the full mining cycle can take over 10 years. Despite the challenges, this method yields millions of carats of diamonds annually, supplying the global market with precious stones hidden in the ocean's depths for billions of years. On the surface, the extracted rock is crushed in processing plants, where massive steel jaws over 20 feet long break the stones into fragments smaller than 2 inches. Each plant can process over 10,000 tons of material per day. After crushing, the rock passes through a series of washing tanks filled with water and chemical reagents. Diamonds, which have high density, settle at the bottom, while lighter minerals are washed away. Once the material is on the surface, specialized X-ray separators are used to identify diamonds based on their ability to fluoresce under ultraviolet light. Magnetic separators work by exploiting differences in the magnetic properties of materials. Diamonds are non-magnetic, while most minerals in kimberlite rock have weak magnetic properties. In these systems, the rock is fed onto rotating drums over 20 feet long, which generate strong magnetic fields exceeding 10,000 Gauss. Magnetic mineral particles stick to the drum's surface and are removed into a separate container, while diamonds and non-magnetic rock residues move forward. X-ray systems are used in the next stage, when the rock is already significantly purified. These systems rely on diamonds' unique ability to fluoresce under X-ray radiation. The stones enter a special tunnel where they are exposed to X-rays with energies of up to 200 kiloelectronvolts. The diamonds begin to glow, and highly sensitive optical sensors instantly detect their location. The system then activates a high-speed air jet operating at pressures exceeding 100 pounds per square inch, which literally blows the diamonds out and directs them into a collection container. The cleaned diamonds are sorted by size, quality, and color. The sorting process is fully automated and managed by operators in specialized control centers. Each operator monitors dozens of X-ray systems using high-resolution computer panels. Modern systems use machine learning algorithms that can adjust equipment parameters in real time for maximum efficiency. If malfunctions or deviations occur, operators can manually change settings or redirect material flows for reprocessing. A single system can process up to 20 tons of material per hour with precision that detects even the tiniest diamonds smaller than 1/10 of an inch. At large diamond mines, dozens of such systems operate simultaneously, extracting hundreds of millions of carats annually. After sorting, the diamonds are sent for cutting, where artisans use lasers and mechanical tools to transform them into precious gemstones. Once cut, they enter the market, sold as part of jewelry or used for industrial purposes. Did you know that over 3 billion cans of preserved peaches are produced globally every year? But how do peaches go from orchard trees to perfect slices in syrup that we all love? From harvest to sealing freshness in cans, this is a high-tech process where every second counts. Imagine a factory filling up to 30,000 cans per hour. Ready to peek behind the scenes of this amazing production? The journey of canned peaches begins in meticulously cared-for orchards. And here is something important. Specific varieties of peaches are chosen for canning. Picture a tree bred to prepare its fruit for a long life in a can. These peaches are cultivated with taste, firmness, and shelf life in mind. They are not just pretty, they are strategically important. These orchards are typically located in regions with warm climates and plenty of sunshine. Peaches love the sun. It is like their secret ingredient. The main peach-growing regions are found in areas with mild and warm climates. California, Georgia, and South Carolina lead the United States in peach production. Among other countries, Italy stands out, especially northern Italy, where a combination of mountains and valleys creates the perfect climate. China is another major global producer. Peaches are grown in nearly all its provinces. Depending on the country, peach orchards can range from a few acres on small family farms to hundreds of acres for industrial producers. In California alone, orchards designated for canning peaches span over 25,000 acres. In Italy, the total area for peach cultivation is approximately 170,000 acres, though not all are used for processing. Growing peaches is a true art. Here are a few key challenges. While peaches thrive in warmth, severe frost can destroy buds or even entire trees. Therefore, cultivating peaches requires careful selection of varieties suited to the local climate. These trees need regular irrigation, but too much water can cause root rot. Fungal diseases like leaf curl and pests such as aphids require constant monitoring and treatment. Peach trees also need annual pruning to ensure optimal fruit growth. This is a complex but essential process. Additionally, peaches must ripen on the tree to be sweet and juicy, but they cannot overripe, as they become too soft for transportation. This means harvesting occurs on a very tight schedule. Most orchards for canning work with peach varieties that have slightly thicker skins and firmer flesh. This allows them to better withstand processing and transportation. Some farmers grow organic peaches, free from pesticides and chemicals. This is more challenging, but results in a premium product that is increasingly popular. Caring for peach orchards is not just work, it is a science. And though it is not easy, the result is fragrant, juicy peaches that we can enjoy even on cold winter days. Harvesting peaches can be mechanized. Tractors with special shakers gently shake the trees, and the fruits fall onto special mats. However, the most delicate varieties are harvested by hand to avoid damage. Did you know that every picked fruit reaches the factory within 24 hours? Here, every minute is worth its weight in gold. Once the peaches are harvested, their journey has just begun. Transporting them to the factory is a crucial stage because these fruits are incredibly delicate. To preserve their appearance and quality, strict rules must be followed. Right in the orchard, the harvested peaches are usually sorted. Damaged or overripe fruits are discarded as they can spoil during transportation. Peaches are packed into small boxes or plastic containers designed to minimize pressure. Often, they are lined with soft materials to avoid damage during transit. Since peaches spoil quickly, they are delivered to the factory as soon as possible, usually within a few hours of harvest. Factories are often located near the orchards to reduce travel time. Refrigerated trucks maintain temperatures at a maximum of 40 degrees Fahrenheit to slow the ripening process and reduce the risk of spoilage. In large operations, specialized systems gently move the fruits into containers. This reduces the risk of mechanical damage and minimizes manual labor. Every minute counts. If the peaches are delayed, they can begin to spoil or lose their appearance. Excess moisture can lead to rot, while insufficient moisture can cause the fruits to dry out. Therefore, containers and vehicles are equipped with systems to regulate these parameters. Each peach is, essentially, a delicate fruit that is easily damaged. Thus, they are packed carefully, with no unnecessary pressure. In some countries, like Italy or the United States, orchard owners use electric mini-tractors to transport fruits from the orchard to intermediate storage. This is more eco-friendly and convenient. Farmers sometimes organize delivery at night or early in the morning when it is cooler. This helps keep the fruits fresh until they reach the factory. In large operations, transportation containers are labeled, so the factory knows exactly which orchard each batch came from. This helps track the quality of every harvest. As soon as the truck with peaches arrives at the factory, the fruits are immediately inspected for freshness and integrity. Those that pass inspection are sent to the first processing stage, washing and cleaning. And yes, this process happens as quickly as possible because freshness is the key to perfect canned peaches. Workers or automated systems quickly inspect the fruits to remove damaged, rotten, or overly ripe ones. Large operations use optical scanners to analyze the external appearance based on color, shape, and defects. Honestly, I would already be exhausted by the endless inspection, and this is just halfway through the peach's journey to store shelves. Even with modern technology, the human factor remains critical. Operators stand by the conveyor belt and pick out fruits that fail the automatic check. Sometimes, only a human eye can catch subtle defects. The fruits are weighed since overly small or underdeveloped ones may not meet canning standards. Washing is not just rinsing with water, but a full-fledged technological process. Peaches are harvested in orchards, where they can pick up dust, soil residues, or even chemical plant care products. After inspection, the fruits enter special rotating drums, where they are gently rinsed with water. Warm water with mild cleaning agents is used to remove even the smallest particles of dirt. Before peeling, peaches are rinsed again, this time with clean water without any additives. By the way, this entire process takes just a few minutes. Next, peaches are immersed in hot water or exposed to steam for a few seconds. This softens the skin, making it easy to remove. This method also helps preserve the texture of the flesh. Then, the peaches go to special machines equipped with rotating brushes or knives that carefully peel them. The goal is to avoid damaging the fruit and preserve as much flesh as possible. The next step involves removing the pits. Special devices carefully cut the peach in half and extract the core. But even here, there are nuances. Some peaches, known as clingstone, have pits that cling tightly to the flesh. These require more precise equipment. Peeled peaches undergo a final check to ensure the skin is completely removed and the fruit's shape is intact. This is especially important for canned peaches made from halves or quarters. After peeling, peaches are cut into halves, slices, or even cubes, depending on their intended use. Here, specialized machines with incredible precision come into play. Did you know some factories have blades that can slice peaches faster than you can blink? Even so, each slice is manually inspected to ensure no defects are missed. Next, the peaches are placed in cans and syrup is added. Depending on the recipe, the syrup can be light, medium, or thick. The most interesting part is that some recipes use special flavorings to enhance the taste of the peaches, and this is the detail you definitely notice when you open a can. The cans are sealed and immediately pasteurized. This means they are heated to high temperatures, which lock in freshness. During pasteurization, canned peaches are heated to approximately 200 degrees Fahrenheit. This temperature range is high enough to destroy harmful microorganisms, preserve the product's freshness, and extend its shelf life, but it does not affect the taste or texture of the peaches. By the way, the entire process takes just a few minutes, leaving no chance for bacteria. The speed of filling cans can reach from 3,000 to 30,000 cans per hour. This demonstrates the high level of automation and efficiency in such productions. After cooling, the cans are sorted, labeled, and sent to warehouses. Sometimes, they even undergo additional inspections, to make sure everything is perfect. Then these cans are shipped to stores worldwide. Did you know the United States, China, and Greece are the 3 largest producers of canned peaches? Additionally, global tasting competitions are held to select the best syrup. Yes, this industry has its own Oscar. So next time you open a can of peaches, remember how many people and machines worked to bring this dessert to your table. You know what? They really nailed it.